Hi everyone, it's time to learn about chi-square. So don't feel silly if you were pronouncing it chai or chi or shy because that's what it might look like. But it's actually the Greek letter pronounced chi. And the symbol for chi is a fancy little X shape. And we use the superscript 2 to signify chi-square. Before I start, I just want to recommend that you watch the Khan Academy video that's posted on iCollege. That would be a good thing to check out, right after this lecture, as well as the reading, of course. And also for chi-square, you'll need the top of the second page of the formula sheet that's posted on iCollege. And so that formula sheet's going to look like this. There's 3 key pieces of information there. You have the critical values chart, the formula for DF or degrees of freedom, and then you also have the formula for how to actually calculate chi-square. And of course, you'll need a handy dandy calculator as well as some scratch paper. Just want to make sure you have all of that ready to go before we get started. Today's lecture is going to be one of those ones where you're going to need to press pause as we go along to actually do the computations. And so just make sure that you're prepared before you proceed. Okay, so the chi-square test we're learning about today is called chi-square goodness of fit test. We typically use this type of statistic when we have categorical data. The chi-square statistic is used to determine whether the data from your sample, and we call this observed data, is consistent with what is to be expected in the general population. So it's called the goodness of fit test because it tests whether the observed data is a good fit to the expected data, to compare those two to see if they're statistically different. So here's a reminder of the steps for null hypothesis testing. First, we state the hypotheses, then we find our critical value, then we collect our data and compute sample statistics. In this case, we will be computing chi-square. And last, we'll make a decision about whether to reject or retain the null hypothesis. So let's jump into our first example. A researcher for an insurance company collects data on car accidents. For a sample of 50 insurance claims, the researcher classifies the cars as high performance, subcompact, midsize, or full size. The general population of cars is made up of 10% high performance cars, 40% subcompact cars, 30% midsize cars, and 20% full size cars. So we want to know if the researcher's observations are the same as what's in the general population. And so we don't know her observations yet, but we'll figure that out later. So essentially, the researcher wants to know if the types of cars that are involved in accidents within her sample of 50 accidents or 50 claims matches the proportion of those types of cars that are in the general population. So first, let's figure out what numbers to expect for each type of car. So in this chart, we see that in the general population, we expect 10% of cars to be high performance. That's what the HP stands for. The sample that the researcher is collecting data on includes 50 cars, so 50 insurance claims. So based on what we know about the general population, we expect that 10% of those cars will be high performance cars. So I need to calculate what's 10% of 50 to get that expected frequency. In other words, it's 0.10 times 50, which equals 5. So that's my expected frequency for high performance. If the researcher's observation is the same as what's in the general population, then she should have about 5 insurance claims for high performance cars in her data set. So let's calculate the rest of these. So out of those 50 cars, we expect 40% of them to be subcompact cars. That's what the SC stands for. So to find the expected frequency for subcompact cars, I'll calculate 40% of 50 or 0.40 times 50, which equals 20. So you can pause here and see if you can calculate the expected frequency for midsize, which is going to be 30% of 50, and for full size, which is going to be 20% of 50. So if you calculated that correctly, you should get 15 for midsize and 10 for full size. Okay, so now we know what the expected frequencies are. Let's move on. It's time for step 1, in which we're going to state our hypotheses. The null hypothesis is that there's going to be no difference between the researcher's observation and what's in the general population, meaning that when the researcher collects her data from those 50 insurance claims, her classifications for the number of each type of car should be pretty close to those expected frequency. When we say that there's going to be no difference, we don't mean a literal no difference as in the numbers will be exactly the same. We mean that the difference is not going to be statistically significant. The alternative hypothesis is that there is going to be a difference between the observed frequency, so the data that the researcher collects, and what's expected. In other words, the number of each type of car represented in the insurance claims won't match up to what exists in the general population. Some types of cars may be overrepresented or underrepresented in accidents. So for step 2, we need to set our criteria. This figure down here is what a chi-square distribution will look like. It's positively skewed. So chi-square values can only be positive or greater than 0. They can range, they have to be higher than 0. So because the statistic, when we calculate it, it's a squared value. So if you ever calculate a chi-square statistic and you get a negative number, you know that you probably did something wrong. So we need to determine our critical value. And to do that, we use a chart. So this is what our chart looks like here. You have this also in your formula packet. And to read this chart, we need 2 things. First, we need DF, which is degrees of freedom. And then we also need to know our significance level. For chi-square statistic, the formula for degrees of freedom is K minus 1. So K is the number of categories. In our situation here, we have 4 categories. Remember, there's 4 different types of cars. So K equals 4. All I have to do is just plug that in really quick. So DF equals 4 minus 1. Therefore, DF equals 3. So our degrees of freedom is going to be 3. For the significance level, you're going to default to using 0.05 unless it's otherwise stated. There may be cases where you're given a different alpha level to use, but if not, then you're going to use 0.05. Now that we know our degrees of freedom and our significance level, we're going to go ahead and use the chart to find our critical value. So our DF is 3, significance level is 0.05. We follow those 2 criteria to see where they meet up. And we get 7.8147 or 7.81 when we round to the nearest hundredths place, which is 2 digits to the right of the decimal point. So what that means is that our cutoff criteria is 7.81. In order for us to reject the null hypothesis and say that there is a significant difference, our chi-square statistic that we compute needs to be greater than 7.81. It needs to be higher than 7.81, and that would make it fall within that critical region. Now it's time for the exciting part. We're going to get our data and compute the chi-square statistic. So in the sample of 50 insurance claims, the researcher found 20 high-performance cars, 14 subcompact, 7 midsize, and 9 full-size cars. So this is the data that was actually collected. This is the observed data, or this we would refer to these as the observed frequencies. So we're just going to plug this information into our chart. So observed frequencies are denoted as F sub O. So F sub O for observed frequencies, and then the expected frequencies were F sub E for expected frequencies. So we have our data. It's time to compute the chi-square statistic. And here is the formula for the chi-square. Please don't be intimidated by this formula. It may look complicated, but we will break it down step by step. Okay, so at the top here, I have the formula as well as the data here just to reference. I like to create a table or a chart like this one to help us break down each step of the formula and solve for chi-square. And you'll see that when we do this process, it's not so scary after all. So here's a chart. In the first column, you're going to have each category. So in this case, we have different types of cars. So we have the high performance, subcompact, compact, midsize, and full size. In the next column, you're going to have your F sub O, which is your observed frequencies. And then following that column, you'll have the F sub E, which is your expected frequencies. So you'll see here that all I've done is transfer the data from the chart that we had, that we started off with, into this chart that I'm using to get chi-square. So now I'm just going to focus on solving for chi-square. I like to break down the formula using order of operations. So the first thing that we'll do is what's in the parentheses. And that's observed frequency minus expected frequency. The next step we will do is focus on that exponent. I know that I'm going to need to square those values. So that's what I'm going to do in that column. In the following column, I'm going to do the next step, which is to dividing by expected frequencies. And then the final step is going to be to get the sum of everything in that last column. And that's going to give me my chi-square value. Okay, so the first step, again, is to subtract we're going to do our observed frequencies minus our expected frequencies. And we're going to do this for each row. So starting with high performance in the first row, our observed frequency was 20 and our expected frequency was 5. So 20 minus 5 is going to give us 15. Next, for subcompact, our observed frequency is 14, expected frequency is 20. So 14 minus 20 is -6. Following that, for mid-size, we have 7 minus 15 equals -8. And then last, observed frequency is 9 minus expected frequency of 10 gives us -1. The next step in the next column is going to be to square those values. So I'm going to take the values that I just found and square them. So for high performance, 15 squared, or 15 times 15 equals 225. For subcompact, we had -6. I'm going to square that. -6 times -6 is 36. For mid-size, we have -8. When we square that, we get 64. And finally, for full size, we had -1. When I square that, I get 1. All right, so we're almost there, guys. Our next step is to divide the values that we just got by the expected frequencies. So for the first row, we have 225, the value, that's the squared value. We're going to divide that by 5. So 225 divided by 5 equals 45. The next row is 36 divided by 20, which is 1.8. The next row for mid-size, we're going to do 64 divided by 15. We get 4.27. And then lastly, we have 1 divided by 10. And that's going to give us 0.1 or 0.10. And now the last step, the last thing we're going to do is add up all of those values in the last column. We're going to get the sum of all the values in the last column. So adding up 45 plus 1.8 plus 4.27 plus 0.10. And when we do that, we get 51.17. And so that is our chi-square value. We have just solved chi-square. All right, last step here, we're going to make a decision. To do that, we're going to compare our chi-square value to our criteria to see if it falls within the critical region. If our chi-square is greater than our critical value, we can reject the null hypothesis. And if it is less than or equal to the critical value, then we retain the null hypothesis. And so let's check out what we have. Our chi-square statistic was 51.17. Our critical value is 7.81. And if we were to look at that, that's obviously greater than our critical value. If we were to put that value on our distribution, it would be somewhere way to the right of this distribution. So it's very clearly in our critical region. It's way higher than our critical value. And so our decision is going to be then to reject the null hypothesis. That means that our result is significant. In other words, the data that the researcher collected on the cars was significantly different from the expected data. We can be confident that her results are different than the proportion of cars in the general population. Now we're going to go through another example. This might go a little quicker this time, but definitely make sure that you take some time to pause throughout the lecture to make sure that you're doing your calculations before you hear me or see me reveal the answers. That way you can make sure that you actually understand the process and understand how to do it for yourself. So let's look at our second example. It states, a student is interested in the proportion of each flavor in a bag of jelly beans. The candy company claims that each bag is expected to consist of 25% apple, 30% cherry, 25% lemon, and 20% grape. The student collects data from a bag of 200 jelly beans. So her sample size is 200 jelly beans, and she wants to see if the proportion of each flavor matches what the candy company claims is to be expected. So let's come up with our hypotheses. Our null hypothesis is going to be that there's no difference between the student's bag of jelly beans, so from that sample, and the general population, which is the expected frequency. And the alternative hypothesis is going to be that there is going to be a difference. There will be a difference between what the student has and what is to be expected. And so before we move on, I'm just going to calculate the expected values. I already have the observed data here. So to do this, we just look at our total sample. We have 200, and we know that the expected frequency for apple is supposed to be 25%. So 25% of 200 is 50. 30% of 200 is 60. For lemon, we had 25%. So 25% again is 50. And then for grape, it's supposed to be 20% of 200, which is 40. So if we're just looking at this data, it does look pretty close, like it's not going to be significantly different. But the only way to tell for sure is to do our statistical analysis and compute chi-square. Okay, step 2 is to set a criteria. Of course, we need our DF, our degree of freedom, and our significance level. In this case, we have 4 categories, so 4 flavors. So K equals 4. All I do is plug that in. So DF equals 4 minus 1. So our DF is 3. We're going to assume an alpha of 0.05 because, again, we weren't told otherwise. And using our chart, we're going to match up the degree of freedom of 3 and a significance level of 0.05. And we get 7.8147 or 7.81 when we round to the nearest hundredth place. All right, so this is our setup. You should make a chart just like this one on your paper. And we have our categories in the first column, our observed frequencies, expected frequencies, and then we have the rest of the chart lets us break down this formula. So our first step again is to do what's in the parentheses. I'm going to subtract the expected frequencies from the observed frequencies for each row. So you can press pause now to calculate that. And here are the answers. Okay, next we're going to square all of those values. So you can pause to do that. And here are all of those answers. And then the next step is to divide those squared values by the expected frequencies. So you can pause to do that. And here are those answers. And the final step is to take the sum of all the values in that last column. So you can pause to do that. And here is our answer. So our sum is 1.19. That's our chi-square. Our chi-square is equal to 1.19. So now it's time to make a decision. Is our chi-square within our critical region? Again, remember that if our calculated chi-square is greater than our critical value, then we can reject the null. If it is less than a critical value, then we retain the null hypothesis. So our chi-square value is 1.19. If we were to put that somewhere on our distribution, it would be somewhere over here. And that is not in our critical region. It is less than our critical value. And so our result is not significant. We retain the null hypothesis. In other words, the number of jelly beans that the student counted for each category was about the same as what the candy company said was to be expected. All right, so here is workshop number 7. Even if you're not planning to submit this workshop for credit, you should definitely still work through it. And I'm going to walk through the first parts of it to get you started. So this is usually my favorite class when I teach this in person, because I usually bring in actual Skittles for everyone to have some hands-on, work with this. But we can't do that, obviously. So you'll just have to pretend that you have this bag of Skittles that you can enjoy. All right. So you have a bag of 15 Skittles, and you want to know, is the proportion of Skittles colors in your bag the same as the expected proportion of Skittles colors? So in this case, I just went ahead and gave you the expected values, the expected frequencies for each color. So you don't have to worry about computing them from the percentages or anything like that. So, so the first step is going to be to state the null hypothesis and the alternative hypothesis. You can do that on your own. I'm going to move on to step 2. Step 2 is going to be to set our criteria. Again, we need our degrees of freedom, our DF, and we need our significance level. So again, degrees of freedom is K minus 1. K is the number of categories. In this case, if you'll remember, we have 5 categories. There's 5 colors: purple, yellow, orange, green, and red. So we plug that in, 5 minus 1. So our DF, or our degrees of freedom, equals 4. And then again, we weren't told otherwise, so we're going to use a significance level of 0.05. So we just look for that in our chart, our DF of 4, our significance level of 0.05, match that up, and we get 9.4877, or 9.49 when we round to the nearest hundredth place. So now we need our observed frequencies. What you're going to do is just use this picture here, or, I already found those. So our observed frequencies, we have 3 purple, 3 yellow, 1 green, 3 orange, and 5 red Skittles. That's what's in our actual observed data. That's what's in our actual Skittles bag. So you're going to go through this process to find chi-square using the same steps we've done in the practice. On the workshop that I posted on iCollege, I already did the first 2 rows for you, but I would suggest that you still try and calculate them on your own, just to, check your answers and make sure you're on the right track. So once you've calculated chi-square, in step 3, you're going to compare it to the critical value, which we already established was 9.49. So based on that comparison, you'll decide whether to reject or retain the null hypothesis. Okay, guys, so here is an example that we're going to do, and this example is going to be very similar. The setup of it is very similar to what you're going to see on the test. So this is a good one to come back to and practice even as you're studying for the next test. So it says a developmental psychologist would like to determine whether infants display any color preferences. The psychologist observes how many seconds an infant spends looking at each color. If a color receives more attention, that means that the infant has a preference for that color. And so we want to know, is there a significant preference among the 4 colors? The observed frequencies, so in this case is the number of seconds. The observed frequencies are presented below. So we already have our data here. We've already collected our data. This is the data that we have. This is the observed data. And these are the questions that you're going to see. These are similar to the questions that you're going to see on the test. So you'll notice that if you read through these questions, it's just walking you through the hypothesis testing process. So the first step is to state your hypotheses. The null hypothesis is going to be that there's no difference there's no preference for colors. So in other words, the frequency for each category, for each color, is going to be equal, meaning that the amount of time that an infant spends looking at each color is going to be the same. And then the alternative hypothesis is that there is going to be a preference for colors. In other words, the frequencies for each category will be different. So they'll look at each color a different number of seconds. And so the next question is, what is the expected frequency for each category or for each color, right? So I know that the null hypothesis is that each category or each color is going to be equal. So like the expected frequencies for each color should be the same number throughout. So to figure this out, I'm just going to add up the number of observations in the observed frequency column. So 21 plus 18 plus 11 plus 10, that's going to give me 60. So I have 60 total observations. So that's 60 seconds. If I divide that by 4, I would get 15. So that's an equal number for each expected frequency. Next, we're finding DF, or our degrees of freedom. The formula again is K minus 1. K is the number of categories. We have 4 categories in this situation. We have 4 different colors. And so DF is going to be 4 minus 1, which equals 3. Again, we're going to be finding our critical value. We know our DF. We need to know our significance level. We weren't given a specific one, so we're going to default to 0.05. So with a DF of 3 and a significance level of 0.05, that gives us a critical value of 7.8147 or 7.81 when I round to the nearest hundredths place. So that means that 7.81 is our cutoff criteria for significance. So now it's time to compute our chi-square. You're going to make this handy dandy chart just like this. You have your categories in the first column where you list each color. Next, you have the observed frequencies, or F sub O, and then you have your expected frequencies, or F sub E. And then you'll break down the formulas. So first you have your observed frequencies minus expected frequencies, then squaring that value, then dividing by expected frequencies, and then finding the sum of all of that. Okay, so in our first column here, you might want to pause, figure this out before I display the answers. And here they are. The next column is we're going to square them. You should pause. And here are the answers for those squared values. And the next step is to divide that. And this is a little bit easier because we're dividing by the same number each time. So you can divide each of those squared values by 15. So you should pause and do that. And here are those answers. And last step is going to sum everything in that last column. So add up all of those values together. So pause and do that. And here is the sum. So our critical, our chi-square is equal to 5.74. So that's our chi-square value. Okay, last step is to make a decision. We do that by comparing chi-square to our critical value. So our chi-square was 5.74. Our critical value, remember, was 7.81. So our chi-square is less than the critical value, and so it's not in our critical region for significance. Therefore, there is no significant difference in color preference. We can retain the null hypothesis. All right, guys, so that's it for the lecture. And this chi-square and all of the statistics that we'll be doing is just one of those things where you just have to practice. You can, there's a practice, you can do the practice problem in the Khan Academy video on iCollege. And there's also a practice set for chi-square. I'll note here that number 3 on the practice set is very similar to what you'll see on the test and very similar to the example that we just did. And so I would recommend practicing that particular problem, number 3 on the practice set, at least a few times to make sure you have it down. All right, guys, that's it for today. Take care and email me if you have any questions.